Alright, welcome back. We're looking at entry to differential equations. There's a whole class on this, actually, like tons of classes on it, probably 4 different classes you can take further in college to do with differential equations. But this section is just about the very intro to that class, which is normally separable differential equations. And even though I'm going to be going through problem 7.2 problem number 5, I just wanted to point out in kind of a more simplified way what separable really means. So you'll notice that we have a dy over dx here, so derivative with y with respect to x, and then we've got a 2x over a 3y squared. Well, this is actually a separable differential equation because what we're going to treat them like is we're going to see, can we get all the y's on the dy side and all the x's on the dx side. So for example, I could multiply 3y squared on both sides, and it'll cancel on this side, and then I'll end up with 3y squared dy dx equals 2x. And we're going to treat differentials this way for simplicity's sake. A lot of math professors won't like this, but I think it is an easier way to visualize it. So even though we can't really treat these as a fraction, in this case we're going to. So we can multiply both sides by dx. And the dx is canceling. What you're left with is 3y squared dy equals 2x dx. And so you've noticed that we've gotten all of our y's on the dy side and all of our x's on the dx side. And that's what a separable differential equation means. So now what I can do is I can take the integral of both sides, and the integral of 3y squared with respect to y is 3y cubed over 3, and then on the x side, the derivative of 2x with respect to x, the integral, would be 2x squared over 2. And it doesn't matter what side you do this on, but you do have to add a plus c. Because remember that when we take derivatives, we destroy information, right? Constants go to 0 with derivatives, which means that, for example, let's look at 3 different graphs that have the same derivative. So the slope is the same on each one of these graphs. So all their derivatives will equal each other. The only difference will be some shift, and we call that shift c. It's a vertical shift that's going to tell us what that constant was that we destroyed when we took the derivative in the first place. So in this case, I'm just going to go ahead and do the plus c on the x side, but you don't need to do it on both sides, just one of them. So now that we've kind of gotten the idea of what that is, let's go ahead and do a more challenging problem. So this is problem number 5 from 7.2. And so the first step with separable is we're going to separate them. So we're going to try to get all the dx on one side, all the dy on the other. Let's go ahead and start out by multiplying both sides by dx. So we'll get dy equals 1/10 square root y cosine squared of square root y dx. Well, we got all these y's on the dx side, so we need to bring them back over. So we can divide both sides by this expression, which will, in fact, just reverse everything. So in other words, now it's going to be 10 over square root y cosine squared of square root y dy equals dx. And so now that we're at this point, we've got our dy's on the we've got our y's on the dy side, our x's on the dx side. So now we can throw up our integration bars. And this side's not too bad. The integral of 1 with respect to dx is just x. And then we're going to put the plus constant for that shifting constant. Now on this side, we're going to need a little bit of trickery. When I see something like this, I'm thinking, well, cosine squared isn't so easy to integrate. But I know that the integral of secant squared is tangent, and cosine squared is 1 over secant squared. And so we could also write this firstly with the 10 on the outside, if cosine goes into the numerator, it becomes secant squared of square root y, and then we're still over square root y, and we're integrating with respect to y. Alright, so now we're going to have to use a u substitution, because think about it this way. If I pick my u equal to square root of y, which is equal to y to the 1/2, then my derivative of u with respect to x, I'd bring down the 1/2 due to the power rule, 1/2 y, and then I'd subtract 1 from my power to the minus 1/2. And so we could multiply the dx over on both sides, and du equals 1/2 y to the minus 1/2 dx. Well, let's try to rewrite this in a way that might help us. So let's multiply the 2 over to this side, and you'll see why in a second. And what we're left with is 1 over y to the 1/2, which is the same thing as 1 over square root y. Well, look here. We've got a 1 over square root y in our integral. This could be useful for getting rid of that. So now we've got our u is square root of y, so u is going to take care of that guy. And then for our du, or our 2du rather, 2du is equal to 1 over square root of y dy. So we've done a proper substitution. To write this, we would say 10 integral of secant squared is still hanging around, but the inside of it is now u, right? Because we picked u to be square root of y. And then instead of writing a 1 over square root of y, 1 over square root of y is equal to 2 du. So we can multiply this by 2 du. We can pull the 2 out the front. 10 times 2 is 20. Alright. And now we're left with that secant squared, which, like I said, is tangent. The derivative of tangent is secant squared, therefore the antiderivative of secant squared is tangent. Tangent of u, 20 tangent of u. And then remember on this side we have equals x plus c. The other side is still equating to this side. So the only thing we have to do now is, the problem didn't ask in terms of u, it asked in terms of y and x. So now we're just going to plug back in our substitution here. So 20 tangent of u, which of course we chose to equal square root of y, equals x plus c. Alright, so this is a differential equations problem. I hope this was helpful, and I'll see you next video.